Hello, so welcome to this video, and if you're new to this channel as well. In this channel I mainly cover physics, and sometimes a little dash of chemistry as well, but coming with physics as core mathematical tools. Therefore I thought it might be helpful to do a playlist on linear algebra. And linear algebra is really the study of vectors and matrices. Now, vectors is something many people are familiar with from high school, so I'm going to briefly review them, but the main purpose of this video is to explore matrix multiplication. So we will be justifying why the algorithm, if you like, that defines matrix multiplication works, like why we define matrix multiplication to happen in the way we say it happens, i.e. how we decide what products of components of a matrix to put together to form our final matrix, and in what order we combine the components of the matrices together. Because matrix multiplication is quite unintuitive, it has very unusual features. For example, if we have two matrices A and B, then A times B will generally not equal B times A. In fact, although we might be able to give using the algorithm, or we might be able to give the output of A times B, it may very well be impossible to find the output of B times A using this algorithm. So matrix multiplication is very, very strange in that the order of multiplication matters, both in what matrix you get as an output, and even if you can define an output from the multiplication of the two matrices. Matrices are also very important in physics, particularly when it comes to quantum mechanics, although you do see them when you're solving kind of linear systems, like when you're looking at coupled harmonic oscillators. So they do appear in a fair few places. And also, matrices are examples of tensors that are a bit more complicated than vectors. So matrices are also a good stepping stone to higher rank tensors, such as those seen in general relativity, like the Ricci-Curvature tensor. So matrices have a lot of uses in physics, but this course, well, if you like, the series of videos will be exploring linear algebra and working chronologically through looking at vectors and matrices. In this video, we'll introduce what a vector is, explain how matrix multiplication works, talk about rotation matrices, and finish by talking about the identity matrix, which is a very special matrix that we'll use a fair number of times in the rest of this series of videos. So, firstly, I'll start defining what a vector is and then mention how a matrix relates to a vector. Now I'll go through vectors quickly because many people are going to be fairly familiar with a vector, although it is worth reviewing the notation we use to write them. So a vector, a good place as a definition of a vector, at least when you're introduced to them at first, is a vector is an object with size and direction. So it has some kind of a length associated with it, and it points in a particular direction. And therefore, often an arrow is used to represent a vector. It's worth saying that's not the only way to represent it. For example, you could have a piece of paper, and a piece of paper has a size, if you like, that is, it has a particular surface area, and the paper is also orientated along a particular direction, like it could be lying flat on the table, it could be plastered horizontally onto a wall, and therefore the piece of paper is another example of a vector, if you think of it that way. But typically vectors, at least certain kinds of vectors, are represented using the idea of arrows. And so we can think of a vector as kind of this blue arrow you can see on the screen. Um, and we can see it's diagonal, so it kind of points horizontally and vertically, and therefore we can split it up into its horizontal and vertical components. And indeed, writing the components is the way you can actually build up a vector. So we say that the vector, well, we say that if we travel from, you know, the start of the vector, and we move a unit horizontally to the right, and move b units vertically upwards, we will end at the very end of the vector. So we can think of the vector as a units horizontally and b units vertically. Now if we want to swap the direction, like talk about a units, but to the left we would have minus a instead of a. For writing a vector in terms of its components allows us to define a vector very clearly without always having to draw it, because here it's fine. But what if I want to say look at a scalar field and think about how that field is changing at every point in space? Well, I can do that by thinking of a tiny arrow at each point in space, but there's an infinite number of points. So if I was going to represent the vectors all visually, I would need to draw an infinite number of arrows, which would take an infinitely long time. So having a way where you can write the components explicitly, and then if you put the components in a particular order, it kind of implies, well, you've got components and they're in a particular order, and therefore you're describing a vector. That's a very ergonomic way to do it. It's also clear when you're just describing one vector, but let's say we replace A with a function and B with a function, we are then describing a whole group, possibly even an infinite number of vectors, with differing horizontal and vertical components. Another thing to note is that here in this vector, we've got our diagonal vector has two components because it has a horizontal and vertical component. And that means that this vector is living on a two-dimensional plane. It's living in two dimensions because it has two components. But the vector itself is a one-dimensional object. Because if you're living on the vector, then to know where you are on the vector, you would only need a single number if you were living on the vector itself. For example, you might say, well, you're in the middle of the vector, or you might say you're at the bottom of the vector or the top of the vector. And we can think of really putting a number line across the vector such that if you live on the vector, you just need to name a number on that number line and you know exactly where you are. So the vector is one-dimensional, but lives in a two-dimensional plane. And the number of dimensions in this case too, but generally the number of dimensions of the space the vector lives on is called the dimension of the vector space. So this vector here lives on a two-dimensional vector space as two components. For many vectors in the physical universe, because there are three dimensions of space, the vector lives in a three-dimensional vector space. And then for things like special relativity or dealing with four-dimensional vector spaces, then it can get fairly complicated. But that's just an introduction to how we describe what a vector is in terms of its components. And what a matrix does is it changes the components of the vector, and by changing the components, it can actually change one vector into another. And then there's two ways it can do this. It can squish or squeeze the vector, so change its length, but keep its orientation preserved, or it can rotate the vector. and thus change its orientation. It could also rotate and squish or squeeze, although there aren't many applications where you're concerned with the matrix doing both. Usually you're concerned with the matrix doing the one or the other, at least in physics. And what we will be concerned with in this video is about matrices that cause a vector to rotate. So it changes its components, and it changes its components such that the length of the vector isn't changed. However, the vector does rotate, so the components do change, but in such a way that the length of the vector stays the same. And in the next video, we'll probably look at the eigenvalue equation, where we'll be talking about vectors which a matrix will squish or squeeze instead of rotating. But this video will be about matrix multiplication and building it up from thinking about rotation matrices. So, as I said, we're going to be building up matrix multiplication through rotation matrices, and the reason we're doing this is there's a lot more generality in how matrix multiplication works if we're thinking of components changing rather than just scaling or squishing components. So it's helpful if we're building up matrix multiplication to be working with rotation matrices. And as a brief aside, we're talking about rotating a vector, but you could talk about rotation of a point on a circumference or even a sphere using rotation matrices. So it can be helpful, for example, in working out the new location of a point on the surface of the Earth as the Earth rotates. There are lots of applications of rotation matrices to things beyond simply just lines. But we're working with arrows here, or one-dimensional vectors, so that's what we'll be focusing on, but it's worth saying that there are, other applications you can generalise this. So, as we've said, we write a vector as a ordered column of components. Traditionally column, because a row of components can look awfully like a set if you're not careful with what brackets you use. And also, we start with column vectors, because column vectors, if we're being really pedantic, represent a particular type of vector called a contravariant vector, and most vectors we're interested in physics, most things that we would initially think of as vectors, like displacement or acceleration or momentum or force, all of these are contravariant vectors. So there is a deeper reason as to why we use a column instead of a row of elements to represent a vector. But for our purposes, we can just say a vector is a ordered set of components put together in a column, and it represents an object with size and direction. And the matrix turns one vector into another. A rotation matrix will preserve the length of the vector, but will cause the vector to rotate about an angle. And usually when we're talking about angles in physics or in mathematics, we use the Greek letter theta, which is that circle with that dash in the middle. So lowercase theta. Even though uppercase theta looks very similar, but that's reserved for something special. So lowercase theta is for angles. And there's a bit of notation here worth talking about in this diagram. So we can see that we have two vectors, x with an arrow over it and x prime with an arrow over it. Now x with an arrow over it, an arrow just means it's a vector. So x with a vector over it, x with an arrow over it just means a vector. It's worth saying that it might have components, an x and a y component, but we represent the components together as a vector as x with an arrow over it. And then our matrix is rotating this vector into a new vector. And generally when we're talking about new vectors, we use a prime in physics, and that really comes into play when talking about special relativity and changing reference frames, although that's really changing your axes rather than the vector itself. But the idea of having different components of a vector is where you would start describing your new components as components of a primed vector, so x prime, say. So if you see a prime, it just means something new. So in this case, a new vector, i.e. the vector we get by rotating our previous vector. And let's say the initial vector had components x and y, and we rotate it by angle theta, and we want to know what the new components of the vector will be, so what the components of x prime will be. Well, the new components we can get by trigonometry. Now, I'm not going to go through the derivation for the new components here too much, because it is simply trigonometry. Now, it's a little difficult to work out what it would be when we put, our vector, our original vector at some angle already from the x-axis. But you can imagine just rotating the vectors in the diagram such that your original vector points along the x-axis, and then it's a lot easier to work out how we would get the new components of the new vector if we rotate that vector. Because if we put our original vector along the x-axis, then it means that it's simplified because it's just a horizontal vector with no vertical component, which if we think in the way that we write the components, means one of the components of the original vector will be 0, which makes working out what the components of the new vector will be a lot more straightforward. So that's what I would recommend if you would like to verify what the new components will be. But I've summarised what they'll be here. And as this isn't a video on trigonometry, I won't be deriving it really. But our x component of our original vector becomes x cos theta plus y sine theta, and the y component, so the vertical component of the original vector, becomes y cos theta minus x sine theta. And you can see here that the new x component depends on the old x and y components, and the new y component depends on the old y and x components. And therefore, when we're rotating a vector, the components of the old vector kind of get mixed together along with trigonometric functions like sine and cosine to give us our new components. So there's a bit of mixing going on. And that's partly what makes matrix multiplication quite strange, that it has to cause this mixing between terms. And if we want to represent our vectors using our kind of component notation, then we have x, y going into x cos theta plus y sine theta, y cos theta minus x sine theta. And that's, the arrow just means it transforms into. And as we've said, the thing that is transforming it is a matrix. And we'll talk about matrices and what kind of properties this matrix will have to have based on the fact it has to do this transformation on the next part of this video. So, to summarise from what we had before, we have our old vector which in component form has to transform through a rotation matrix, which I've used the symbol R to represent, into our new vector, with the new vector component shown explicitly on the screen. And we want this to happen through a rotation matrix R. Now, we can think of, the easiest kind of operation to really think of when we're causing a matrix to turn a vector into another vector is multiplication. So we're going to just hypothesize, and we're free to do this at the moment because we haven't really been specific about a matrix at all, that we get a new vector by multiplying the old vector by a matrix. And that's the bottom equation we have in the blue box. And so if we consider now what properties this matrix will have to have, so as we've said, the matrix needs to mix components of the old vector to get the components of the new vector. And using here the idea that primes represent the new vector, so x prime is the horizontal component of our new vector, and the horizontal component of the new vector depends on the horizontal component of the old vector and the vertical component of the old vector. So x prime depends on both x and y. And this idea of the horizontal component of the new vector depending on both the horizontal component and the vertical component of the old vector, when we're thinking of the transformation through rotation, has quite significant impacts on what kind of rule we can give for matrix multiplication, such that, when we multiply our vector by this matrix, we get our new vector. We can also, if we look at the new vector, if we think of x and y as independent quantities, and it makes sense to do this because our original vector had components x and y which were quite independent. So we can think of all x terms as being independent from the y terms. And so we really have, if you like, in the horizontal component of our new vector, so the x cos theta plus y sine theta, we really have two distinct parts referring to x and part referring to y. And similarly for the vertical component of our new vector, again we have two kind of distinct terms, and therefore we can think of there being kind of four terms that this matrix is going to have to worry about, and the easiest way to cause this to happen is to just say explicitly our matrix needs to have four components, four terms within it. And the order of those terms and how we define matrix multiplication will ensure we get the right combinations of terms to get the right components for our new vector. And we don't have to do this, but again, we don't really know much about matrices yet. So we're kind of free to do this. The easiest way to have the four terms is to go, well, our old vector already had x and y components, so our rotation matrix doesn't really need to have x and y in it. In fact, if our matrix is going to describe rotation, we just want functions of angles really in it. We don't want to refer explicitly to a particular vector, because the rotation matrix should depend on the angle something is being rotated, not on the thing it's rotating. And therefore, our rotation matrix needs to have four terms, but those four terms should be functions of angles. And if we just write the terms in the order we see those terms arise in the components for our final vector, we can see a natural way to write it is just to have cos theta and sine theta on the top and minus sine theta and cos theta on the bottom. Now you might ask, what's the formal justification that we can do this? Well, the answer is really we just can, because we're building matrix multiplication, but providing we're not contradicting anything in maths, we are free to say how we're writing things. So, to summarise so far, we've said for convenience this is our rotation matrix, although we've kind of partially justified it in terms of the idea of it having 4 components, referring solely to trigonometric functions. So it's kind of, in a fuzzy way, if not justified, we've justified that that's a sensible way to go forwards as we're building up our definitions of matrix and matrix algebra. And the rotation matrix should multiply my old vector, which has components x and y, into my new vector, and we've shown explicitly on the screen the components of my new vector. So now we're beginning to get something quite specific. So we've talked about essentially giving a form for our rotation matrix, and we've also talked about writing the components of our new and old vector. And we mentioned that we get our new vector by rotating our old vector by this matrix through multiplication. Now, you might wonder whether there's any more points we can deduce about a matrix and matrix multiplication before we go on to define it generally. Well, one last point is that if we're thinking of multiplying two things, it's a lot easier to think about how we can multiply them if both those things are the same type of thing. For example, it's easy to work out what 4 times 4 would be, because 4 is a number and 4 is also a number. Or I really should say, if we're multiplying 4 and 5, like 4 is a number, 5 is a number, so it's easy to imagine what 4 times 5 should be. It should give us another number. However, it's very hard to work out, say, what an apple times a banana would be, because an apple and a banana are 2 different types of objects. So really, in multiplication, we want both types of objects to be the same. And so the object that we're multiplying to get our new vector is a is a matrix with 4 components, and a vector with 2 components. So if we want those 2 objects to be the same, we need to ask, well, could a matrix be a vector, or could a vector be a particular case of a matrix? Well, clearly a matrix can't be a vector, because we said a vector is a ordered list of components written in a single column, and our rotation matrix clearly doesn't fit that. So a matrix can't be generally an example of a vector. However, vectors, based on what we said so far, there's nothing stopping us saying vectors could be a particular case, a particular type of matrix. And so, as we said, to make multiplication easier to make sense of, and to also generalise what we're doing to other cases where we're multiplying things with matrices, it's easier if we stop thinking of a vector as a vector and start thinking of it as a special case of a matrix. So we, using this, now start to get a bit more specific about a matrix. So we define a matrix to be an object with n times m components placed in an order such that our overall object, the matrix, has n rows and m columns. Now that sounds a bit abstract, so let's go through examples based on our vectors and our rotation matrix. So, for example, a vector with n components has only one column because all the components go on a single column, but it will have n rows. So a matrix is a vector is a n by 1 matrix. And our rotation matrix, because it's got 2 rows and 2 columns, hence 4 components, is a 2 by 2 matrix. We sometimes call it a square matrix because it has as many rows as it does columns. And square matrices have particular uses because of this, which I'll probably talk about in more detail in another video. So, using this idea, really the rotation of our vector living in 2-dimensional vector space is just really a special case of multiplication. We're multiplying a 2 by 1 matrix by a 2 by 2 matrix, and we're getting out of that another 2 by 1 matrix. And we want to define matrix multiplication such that this will always be the case, because a matrix should turn one vector into another vector, but it shouldn't generally change the dimension of the vector. Well, I mean, you could rotate it out of the plane, but we're not worrying about that. And because we're talking now about vectors as a specific kind of matrix, it's worth thinking about how we write the components of a matrix and then how we apply that also to vectors. So if we start with the components of a vector, so we write the components of a vector by firstly writing the symbol, we're going to start with looking at the components of a matrix, a general matrix, say a 2 by 2 matrix, like the rotation matrix, and then we'll move on to vectors. So, if we're thinking of where the component goes in a matrix, we firstly say what row it's in and then what column it's in, using numbers. And those numbers are subscripts that we put at the kind of like bottom, well, kind of like to the side, but you know, lower down, our symbol that represents our overall matrix. So if our overall matrix is R, then R11 is the component of R that is in the first row and the first column. So it's going to be cos theta. Now R12 is the component that is in the first row but the second column, so it's sine theta, and you can do a similar thing for the bottom 2 components of our rotation matrix. Now we can do a similar thing with vectors, but because vectors there's only one column, because we put all the components into a single column, with vectors the kind of number we put for the column is the same for all components, and because we're starting ordering from the number 1, we say that kind of like all components lie along the first column because it's the only column and we're starting with number 1. So x11 is the top component, the component in the first row of our matrix, which is A, and x21 is the component in the second row, so the bottom component, which is B. And so the benefit of writing components of a vector in this way is we make a vector in terms of how we describe its components just a specific case of a matrix, and we don't really treat them any differently, and that's very important if we're going to define matrix multiplication and think of rotating a vector as just an example of matrix multiplication, because we would like to generalize this to talk about multiplying matrices generally, which is what we'll come on to in the next slide, and then we'll be talking about a specific kind of matrix called the identity matrix, which is special because of a special property it has in terms of matrix multiplication. So it's worth saying in the previous in the first part of the video, I made a clear distinction between a vector and a matrix. In the part of the video that has just been done, and just kind of like been sharing with you, unifying the idea of matrices and vectors together, we talked about how a vector is a specific example of a matrix. So from now on, for at least this video and possibly my other videos, in this kind of set of videos on linear algebra, I will, generally speaking, not really distinguish between a vector and a matrix. Maybe that might change for other videos, but at least for this video, I will just refer to a vector as a particular kind of matrix. Just worth saying before we go any further with defining matrix multiplication. So, as we said, we can talk about the rotation of a vector as an example of matrix multiplication, where we have a 2 by 1 matrix, we multiply it by a 2 by 2 matrix, and we end up with another 2 by 1 matrix. And because of how we decided to write the rotation matrix, and also using trigonometry to work out the new components of the new vector from the components of the old vector, this matrix multiplication has to result in the equation in the blue box we have here, where we've wrote the components of our matrices explicitly. And for this, if we're generalizing it, we can think of our rotation matrix as just a matrix A, our original vector as a matrix B, and our output matrix, our new vector, as a matrix C. And then we can write the components of C, our new vector, in terms of the components of A and B, using the kind of notation we developed or mentioned not too long ago. And doing that, this is what the elements of my output matrix or my new vector will be. And we see, for example, that C11, so the top components of my new vector is just going to be A11, B11, so cos theta times x, plus A12, B21, so sin theta times y, and you can do a similar thing to verify the C21 expression is works in accordance with what we've got for when we wrote the matrix multiplication with the components written explicitly. Now, I will take a moment to make sure that you're happy with this, because now we're going to define matrix multiplication as a generalization of this. So, one thing to note is that there's something a bit symmetrical in C11 and C21. The way that we've got the components of the new matrix, that there's a kind of symmetry in how we're getting these new components. And the way we're going to generalise this will really capitalise on this symmetry. So don't panic if this looks strange, it will at first. I'm going to kind of break it down a bit here. But what we have in the blue box at the bottom of the screen is an expression, a general expression for the components of a new matrix C if you're multiplying A and B. And this expression defines matrix multiplication. We define A times B as resulting in a matrix C according to this expression. Now, one thing to note is that um, there's this strange kind of almost E thing, and that means we're summing over something, and we're summing over an index k. Now k is called a dummy index, because we're summing over it, and what summing over means is we essentially add components of A and B multiplied together until we run out of possible values of k, essentially. So, for example, because of the matrices we've been dealing with, k can be 1, it could also be 2, but it can't be 3 or 4. Essentially, the matrices aren't big enough for k to go beyond 2. Therefore, we're summing over the situations where k is 1 and k is 2 in all our expressions for the components of our new matrix. For example, C11 is summing two products, summing kind of like 2 terms together, and each term is a product of 2 elements. And in one of these terms, k is 1, and in the other term, k is 2. And we can't go beyond that because the size of our matrices won't allow anything beyond that to be well defined. So C11 is just the sum over k of A1k v k1. And k can be 1 or 2, so C11 is just A11 B11 plus A12 B21. And that's kind of how the summation works, and you can do a similar thing to get k to 1. So I would take a moment to just make sure you're happy that this generalisation does encapsulate our expression for C11 and C21. And once you're happy with it, I would like to talk about, now we've defined matrix multiplication, what restrictions this multiplication places on what matrix multiplication looks like in terms of what properties does it have. So does A times B produce the same thing as B times A, and can we use it to guarantee that the rotation of any vector will produce another vector? Well, firstly we can see that if we have 2 matrices A and B, then the matrix we get as a result of matrix multiplication, C, will have the number of rows of A and the number of columns of B. And because of that, and A, when we're doing rotations, is a 2 by 2 rotation matrix, and B is a vector, so in this case a 2 by 1 matrix, we can see that we'll always produce another 2 by 1 matrix thanks to this. And therefore, this way of doing matrix multiplication keeps intact the idea that when we rotate a vector, rotating doesn't cause it to magically change into a 2 by 2 matrix or a rotation matrix. No, we're still left with a vector, which is something we really want to have, because obviously we can rotate an arrow and the arrow doesn't suddenly vanish and become a rotation matrix. It's still an arrow, it's still a vector. So that's very important to make this mathematics meaningful. But the other thing to note is that for the matrix multiplication to work, because k is going to have the same value for both A and B within a single term in the terms we're summing to get our components of C, because of this, to multiply matrices together, the number of columns of A must match the number of rows of B. And a result of this is that whilst we can do a 2 by 2 matrix times a 2 by 1 matrix, we can't meaningfully define a 2 by 1 matrix times a 2 by 2 matrix, according to standard matrix algebra. And therefore the order in which matrices are multiplied really matter. It not only affects what result you get, it affects whether you can even define a output matrix from the matrix multiplication. So we say, using technical jargon, that matrix multiplication is non-commutative. That is, if you multiply two matrices, to work out what you'll get, you need to know the order in which you're going to multiply them. So, for example, we cannot work out the output of these two matrices multiplied in this order in this blue box, where we're trying to do the vector first and then the 2 by 2 matrix after. So that's an important thing to keep in mind with matrices, and the non-commutativity is a very unusual property. It does have physical application, such as Heisenberg's uncertainty principle in quantum mechanics. You can also think of it as the order of rotations. If you have multiple rotation matrices, the order of rotation matters, and you'll get a different output if you change the order of rotation. If you're considering rotating about multiple planes, that is. So that's really a summary of matrix multiplication, and it's worth saying we've developed something quite general, but now I'm going to talk specifically about the identity matrix, which is very special, and we'll be using it a lot probably in future videos. So the identity matrix is very important because it's kind of the equivalent of the number 1. And the number 1 is important because for real numbers, all real numbers are built up from the number 1. And 1 has a very special connection to the idea of multiplication. And similarly, there's something that takes on the role of 1, but for matrices, called the identity matrix, and it has a very important property in relation to matrix multiplication. But let's think about why 1 is significant if we're thinking of multiplying real numbers, and then we'll just translate that to matrices. So if we consider a real number j, so j might be 2, it might be 4, it might be 5, it might be pi even, whatever you want, whatever floats your boat. Well, 1 is defined such that this number, j, times 1 will always equal j. So pi times 1 is pi, 2 times 1 is 2, 5 over 101 times 1 is 5 over 101. So 1 doesn't actually change the number, it keeps the number preserved. So similarly, if we have a matrix A, and we're saying the identity matrix should be a matrix equivalent to the number 1 for matrices, then we define the identity matrix to be a matrix such that when we multiply the identity matrix with any other matrix, we get back that matrix. So the identity matrix times A is going to equal A. And this timesing is defined by matrix multiplication as we've defined it before. And this here is our expression for matrix multiplication. So we can now actually work out, because we defined the identity matrix quite abstractly, but we can work out its components based on the requirement that I'm just going to call, oh no, I won't call it I, because that's used for other things in maths, but the identity matrix times A gives me A, and matrix multiplication is defined as we have it here. And so writing our identity matrix times A gives me A in terms of how we define matrix multiplication generally, we end up with this definition for the identity matrix. And this is telling us about the components of the identity matrix. And we can now think, okay, what components must our identity matrix have such that this equation holds for any component of our matrix A, so holds for all values of A, ij. Well, this works essentially where we can go, well, K becomes J, that way AIK becomes AIJ, and we get rid of the summing such that we're just left with AIJ equals AIJ. So, in other words, we want our identity matrix to equal 1 when K is J. That way we can just replace AIK with AIJ. But we want the identity matrix to be 0 otherwise, because we want AIJ to always equal AIJ. Because by definition they have to be equal. Well, you know, AIJ has to equal AIJ anyway. A component of a matrix has to equal itself. And therefore, our identity matrix would be a matrix where a component which is in the same row as it is in the column in the same column, that component has a value of 1. But all other components are 0. And I'll show you what that looks like on the next slide where we'll be finishing this video. So, essentially what it looks like is what we call a diagonal matrix, where all diagonal terms are 1. So a diagonal matrix is a matrix where essentially all terms, apart from terms where the row it's in and the column it's in are the same, so all terms apart from terms of what we call the leading diagonal are 0, and because it's an identity matrix we also require that terms on the leading diagonal are equal to 1. Now this is a 2x2 version of the identity matrix, but you can generalise it to a 3x3 identity matrix or larger identity matrices. So this video has been on matrix multiplication. We've built it up from considering rotation matrices. In the next video I'll probably talk about eigenvalue equations. And eigenvalue equations will make specific use of this identity matrix, although this identity matrix occurs a lot, so I might even talk a little bit about using quantum mechanics. Although I am trying to broadly keep this series of videos separate from the physics, such that we can really focus on the maths and give the tools needed such that, you know, anyone watching this can then apply them to the physics they're doing, or would like to learn. This is the first video in the series I hope to make. If you enjoy this video, you know, consider maybe liking or sharing it, or if there are certain parts you would like me to go over, or certain topics in linear algebra you would really like me to include in the series, let me know in the comments below. And I really hope that this kind of video is going to be helpful to some of you, hopefully to all of you, but there'll hopefully also be some which kind of would like to brush up on linear algebra. And a good motivation to do this is that matrices are used a lot in quantum mechanics, but you will also find them in other places of physics. So I hope this video has been helpful. I know it's rather long, but I wanted to justify matrix multiplication rather than just say, well, here's the rule and here's the properties we can get from it. So I hope it's been enjoyable, and hopefully see you for another video soon.